personal against them, but I just don't like the idea. Nobody knows what I'm talking about. Anyway, so last time we were talking about these very complicated converters with lots and lots of switches, right? So can somebody tell me what is the switching frequency in this kind of converter, in this kind of topology where we see these different levels? What's the switching frequency of any of the switches? Yeah, equal to the fundamental frequency that we're trying to achieve here, right? So, and this is one way to run these complicated converters. You can even do that with the multi-level converter to some extent. It becomes a bit more challenging to do it with a multi-level converter, because here what this node is doing, for example, is it's if current is coming in or out of this node, what will this be affecting? Current is coming in and out of this node, right? Because we said current will come in and out of here. If it comes in and out of here, where is it coming from? It's going to be coming maybe through this switch and through this diode and here, maybe through this capacitor or this capacitor. So if current is coming in and out of a capacitor, it changes the voltage levels of the capacitor, right? And we are relying on the fact that this is VDC over 2 to be able to produce half VDCs, right? So sometimes it becomes, if you're switching at fundamental frequency, it's going to be hard to control the actual voltage of this capacitor. So you need to maybe add more pulses when you utilize more complicated topologies such as this. The H-bridge cascaded, it's okay, you can, because the voltage across the capacitor is the same as, it's the DC voltage. You have your H-bridge, this, the capacitor here has a stiff voltage across the source, right? So nothing will change. The capacitor voltage will not really change much, maybe very little ripple, right? But in this case, that's not true. Here I'm actually, anytime I have the two middle switches on and current is coming in or out, I'm affecting the value of voltage of these capacitors. So people started working on, more advanced ways to switch power converters. Not just for the sake of the multi-level converter, but to be able to come up with advantages similar to the stepped voltage waveforms, but with low complexity converters. Like I would like to use only a full bridge converter, not 5 full bridge converters, to produce a waveform with decent quality. So the way to do that is add multiple pulses, right? We saw that we can add that slowly, 1 or 2, 3 pulses by solving some equations. But what people started realizing is that's not really going to work, especially when you have large number of switches. It's not really going to work. So, and when you want to change voltage and frequency all the time, right? You want to keep it controllable. So these converters where we were solving for different angles, we had to solve every angle. We had to solve the values of the angles to be able to come up with the pulse widths to control the value of voltage. So you would have to have a huge lookup table with an infinite number of steps for the various values of output voltages that you want, and you solve for the corresponding angles, and then you put that in the processor. So that's one stupid way to implement something like that. But if you come up with a nice simple way to produce multiple pulses that creates a nicer sine wave. That's what people started working on a lot. And last 10 years people spent a lot of time on what is called pulse width modulation, right? So that's the motivation behind doing a lot of work on pulse width modulation. So simply speaking, there are you can classify pulse width modulation into two sort of technologies, or two sort of formats. Bipolar, meaning the output voltage is either VDC or minus VDC. Let's say this is for the full bridge. I'm talking about the application of pulse width modulation for the full bridge inverter, right? We know that the full bridge inverter, if I switch on the two opposing switches, I get VDC on the load, or minus VDC if the other two switches are on, right? VDC and then minus VDC. So, but if I switch the top two switches or the bottom two switches, I get zeros, right? If I don't use that, then I just get a VDC and minus VDC kind of output, and that's called bipolar switching. It's fine. How do you produce bipolar switching? One way to produce bipolar switching is to compare your reference waveform that you would like to create, which is this sine wave here. This is an indication of what? duty cycle of the converter, right? Again, if we look at our, if I look at my basic buck converter, I will draw it using my single pole double throw sort of representation. We said that the average value of voltage here is what? What's the average value of voltage here? If this is controlled with a duty cycle of D, and this is VDC, D times VDC, right? So that's the duty cycle here, right? So can I make this D? And typically in chapter 6 we were making this D what? Specific values to produce a specific output voltage, right? Fixed. Fine, we vary it because we want to make sure that we control the voltage at the output, even if the load changes, right? But I can also make this very sinusoidal, right? Can anybody prevent me? If I make this D very sinusoidally, what is the range of variation of D? D is duty ratio. What is the range of variation of D? 0 to 1, right? Duty cycle can only vary from 0 to 1. So 0 here and 1 here. And I make this variation, can I make it negative? I cannot make it negative. Duty cycle cannot be negative. I can make it only vary between 0 to 1, right? So if I do this, I make the duty cycle vary this way. I produced an output voltage here that looks like a sine wave, but it's not really, because here it's all positive, right? This between these two nodes, it's all positive only, right? Am I creating negative? I'm not creating negative, right? I am not creating negative here. But is there a way to create to make AC out of this? Can somebody suggest a way to create AC out of? Maybe add another one. So what if I do this? Add another switch here. This is also controlled. Let's say I call this D prime. I will also create an output voltage here called that's D prime times VDC, right? Because this is also the DC voltage across these two switches. Correct? Yes? No? How can I vary D prime so that I can get an output voltage here between these two nodes that is sinusoidal? Yeah, I want to make the difference sinusoidal. So one way to do it, for example, would be if I control D, so this is D. How about if I make D prime look like this? I make D prime look like this. You can do that, right? Also between 0 and 1. Nothing. No. What's the difference between these two waveforms? Because the difference between them will appear between these two terms, which is my load, basically, right? So what's the difference between them? Here the difference is 0. Difference here is 0. Here the difference is 0. How about here? It's 1 minus 0, 1. How about here? I'm taking this minus the red minus the blue, right? So it's 0 minus 1, so it's a negative 1. So I can produce a nice sine wave like this, right? So this is a nice way to produce an AC output waveform with a full bridge converter. Can you? Of course. D. How do you create D? Yeah, that's the next step. So how do I create D now? That looks like this. D is what? D is an input. It's an input. When I talked to you about the looking at the circuits that we developed in chapter 6 from a control of 420 perspective, I wanted you to input was duty cycle, output was voltage, or input was duty cycle, output was current. So this is an input that you create. So how do we create that in industry today? How do we create that? Just with a duty cycle reference that's coming from, let's say, a potentiometer or a processor or whatever you want. You can have a processor here, a microprocessor, and this microprocessor has a digital to analog converter, and then you have a variable here that you're creating that's analog. right? 0 to 3.3 volts, for example, where 0 is, your 0, and 3.3 volts will correspond to the 1 in your duty ratio, right? And then I would like to switch, right? Yeah, fine. I know. Now I can create my D and D prime, right? I can create my D and D prime from a microprocessor or whatever, right? I can, processor. You can have an analog circuit. You can have, you've taken circuits where you've taken a square wave and you filtered the square wave to create a sine wave, right? Maybe in what, in 214, I think you've taken op-amp circuits. So where you've taken a square wave and maybe converted that to a sine wave by putting a filter to eliminate all the high frequency content, right? You would do that. This has high frequency content. I can eliminate the high frequency content due to these sharp transitions, and I can create something that looks like a sine wave. So it's easy to create this D prime or the D. I can create the D and the D prime that I was looking at before. I can create them. But now I need to take that and translate it into variable pulse width, right? Because how does a DC-DC converter operate? I take a duty cycle, and if I want the duty cycle to be 0.3, I produce a pulse that has a width of 0.3 of the full switching period, or this is 0.5 of the full switching period, right? If D is equal to 0.5, then the width of this pulse is T. So T over capital T has to be 0.5, right? So I would like to create these pulses now that are controlled by duty cycle. What's a good way to do that? Actually, you like the dark, huh? No, no, you don't like blue, right? Yeah, you like the yellow on the black background is next screen. So how can I do this? Simple comparator, right? If I compare my reference duty cycle to a triangular waveform, right? Here. Also, the triangular waveform has to be between 0 and 1. Okay, I take my reference, my triangular waveform, and I compare that to my reference duty cycle. And then, what will the comparator do? Here, this comparator, because I put this D on the positive end, anytime D is greater than the triangular waveform, I will get a high. Right? Anytime D is less, I will get a low. Yeah, D is a continuous waveform. D is the actual D. That's why you can do linear control with this stuff, right? Because D is actually a nice continuous waveform. You're converting it later to a nonlinear circuit because the power supply is actually a nonlinear circuit. But from a control perspective, you produce the linear control variable, right? So no, D is a continuous waveform, right? But I need to convert this continuous waveform to something that resembles pulses. How do you do that? The easiest way is a comparator. Of course, you can do all of this inside the processor. You don't need to create a triangular waveform and then have a processor here. Because inside the processor, I can create it, typically inside the processor you would have timers, right? You've taken 350 or 449, right? You would have timers inside the FPGA, right? Yes, no? You will have a timer. This timer, you can set it to count from 0 to 1000, and then you can make it count. This is another thing. You can make it count from 0 to 1000, for example, and 1000, let's say 1024 if it's a 10-bit timer, right? If it's a 10-bit timer, you count from 0 to 1024. If it's a 12 bits, it's what? 0 to 4096? 2 to the 12, what's that? Or 2048? What's 2 to the 12? Come on. Huh? Yeah, 4096. So if it's 10 bits is 2000, and 10 bits is 1024. 12 bits is 4096. You can you tell the timer. You go inside. You put inside the register. You say, okay, I want you to count from 0 to a certain number, and then after that, what do? Do you count down, or do you reset the timer? You tell it to do that. You program this, so you can make it look like this, or you can make it look like this, or you can make it look like this. This is counting up down. This is counting from 4096, for example, to 0, and then resetting the timer. This is opposite, from 0 to 4096, and then resetting the timer, right? Each one of those you can take and compare to your duty cycle. Each one will produce something that looks different, right? One will produce something that is centered. Let's say this is your switching period T. If you're counting up and down, down, your pulse width here is going to be centered. How about if you're like this, and you're comparing? It's going to be on the left-hand side, but the width will change. This one will change, left and right. How about if you are doing this? It will be touching on the hand side, and the width will change depending on your comparison. At the end of the day, did I change? What's the duty cycle? Here, here, and here. What's the duty ratio? Huh? The same. The duty ratio is the same. It's the T on over T off. It's the same. T on over the full T. So it's the same. But what will change? The harmonic content. Because remember, Fourier series will depend on the angles. Remember, we looked at you change the angles, and then you will change the harmonic content. So that's what people worked on. Okay, I can produce something with better harmonic quality. People start working on these things. And can you imagine if you do that on the multi-level inverter? The number of switches, the number of types of the combinations that you can do, immense amount, right? So, and then people did a lot of work on, okay, I can come up with an algorithm to switch and produce a nice pure quality sine wave, at the same time help you balance your capacitors. They take into consideration the number of states where you have the inner two switches on and the direction of current, and they try to balance those so that you always have a balanced capacitor voltage. For example, right? There's research. You can try to optimize so that you reduce the number of switching that is happening, while creating a reasonable harmonic output. Right? I can create VDC in several ways. I can create VDC by switching 2 switches or 3 switches or 4 switches, which is better for harmonic output, right? Or which is better for switching losses, or which is better for harmonic output or switching losses. The main common mode voltage is a different one, but we didn't talk much about that. But so anyway, so this is what. This is one simple way. The simplest way to produce a pulse width modulated waveform is a comparator and some analog inputs. Put a triangular waveform, compare it with a continuous waveform. If this continuous waveform is a sine wave, you will produce something that looks like a sine wave. If it's a DC waveform, you'll produce something that looks like a DC waveform. At the end of the day, a power converter is an averaging circuit. That's what it does, right? It produces D times VDC. Right? These two switches, when you put them across a stiff voltage and you have a stiff current coming out, what is the voltage between the output node and the reference? D times VDC. You take this D and do whatever you want, right? You can make it DC, sine wave, whatever you want. So this is called a pulse width modulator, right? This is the simplest form of a pulse width modulator. Just an analog comparator with a triangular waveform. Okay, is it good to make this triangular waveform high frequency or low frequency?
Low frequency versus the
Hmm?
rising time of the op-amp.
Sure, then if you want to make it high frequency, then you have to make sure you have to get a very fast op-amp, because the slew rates and rise times of the op-amp. That's one thing, sure. The other thing is, switching losses, right? If you make this low, triangular waveform, low frequency, then your switching loss will be less. But you will have less number of pulses per switching period, which may not be good for your harmonic content, right? So it's a power quality issue versus a, switching loss and efficiency type, compromise. Right? So there's no right answer. I was trying to see if you can tell me right or wrong, and there's no right answer to use this method or this method. It depends on the power quality, right? It depends on the power quality that you get at the output here. And you can analyze and look at what people are doing. So with bipolar switching, I did not utilize my zero states. And here, how does bipolar switching work? It's comparing my triangular waveform to this sine wave. Anytime the sine wave here is greater than my triangular waveform, I switch on switches 1 and 2. Anytime the triangular waveform is higher, I switch on switches 3 and 4. Here, this is my 1 and 2 will put VDC across the load. 3 and 4 will put minus VDC across the load. Right? So this is how bipolar switching would work. Right? I did not utilize the zero states. Good or bad, it's one way of switching. Right? We will look at the harmonic content of both techniques here. But I think you can guess here, right? So this would be called unipolar switching. With unipolar switching, we would have two carrier waveforms, like I went through the exercise of producing two carrier waveforms, and these two carrier waveforms would control the various switches. So switch S1 would be on when the sine wave is greater than the triangular wave. So this is the V sine, and this is minus V sine. So these they're 180 degrees of each other, and then each of them will be controlling the set of switches. So S1 will be on when V sine is greater than V triangle. So V sine here is greater than V triangle, this triangular waveform. So S1 will be on. So S1 is on. What else is on if V sine is greater than V triangle? Or what else will be on during this period? If this is minus V sine, so if minus V sine is less than V triangle, S2 is also on. So this is minus V sine. This is minus V sine. And then it is here greater than minus V triangle. So S2 is not on at this time. But here, beyond this, beyond it, with a little bit here, the sine is greater than V triangle, and the minus V sine is less than the minus V triangle. So S2 will be on here, right? So then basically this logic will control the switches, the four switches. The idea is here I'm not using only the S1, S2, and S3, S4 like the bipolar case. Here I'm adding the zero conditions. So when I have zeros, what does this mean? When I have 0 for VA, VA is the voltage between here and this node. It means that either S1 and S3 are on, or S4 and S2 are on. So let's look closely at one of them. So that's the background. So here, this VA has 0 here. Right? So VA has 0 in this zone. Right? What's happening here? What's happening is that V sine here is less than V triangle, right? This is V sine and this is V triangle. So V sine is less than V triangle, so V sine is less than V triangle, so S4 is on. Right? So V sine less than V triangle, S4 is on. If S4 is on, this is on. Right? We obviously know that if this is 0, then also S2 should be on. If you want to get 0, right? If you want to get a 0 across the output, right? S2 should be on, correct? This is VA. What am I trying to? VA is 0. No. So if S4 is on, VA is 0 automatically, right? If S4 is on, VA is 0. How about the line voltage? For the line voltage to be 0, S2 has to be on. So let's see, the line voltage is VAB. So during this part, the line voltage is also 0. Right? If the line voltage is 0, then I guarantee you that this condition will also be happening, right? So let's see if this is happening. So here, minus V sine, which is this waveform, is less than V triangle. V triangle is up here, right? So minus V sine down here is less than V triangle, and that's why S2 is also on. And if S2 is on, and S4 is on, S2, S4 is on, then the voltage across this load is 0. S2 is on, S4 is on. This load has 0 voltage across, short circuit across the load, so it makes sense that the output voltage VAB has a 0 here, right? So basically what we did here was utilize the 0 states in the converter. Before, in the bipolar, we were not utilizing the 0 states. Was I producing something that looks like a sine? Yes, I'm producing something that looks like a sine, obviously, because here I have something. Sine is what? Small average value, larger average value, small average value, negative average, opposite average value, small average value. Yes, here this is obviously, I have large values of pulse width for DC. I have VDC here for a long period of time, VDC for a long period of time, less period of time, less period of time, a lot less period of time. Actually, I have minus VDC more than I have VDC. So I've switched the polarity, right? Because again, the power converter is an averaging device. So it was average. If you look at the average value of these numbers of the voltage here, it's a positive average. Here it's a negative average. So I've created this, and the same thing with unipolar switching. But it's a lot more obvious here that I cannot go negative, right? There's no possibility that I'm not including the negative portions of the waveform at all. So I can easily control the output voltage to look more like a sine wave with unipolar switching. If I utilize these 0 states, I can make it look more like a sine wave. So from a harmonic perspective, which do you think is better, the unipolar or bipolar? Unipolar switching will be better from a harmonic perspective. So if we look at, of course, there are other ways besides unipolar and bipolar. Some people, for example, came up with, okay, how about, let's say if you do this. Let's say I keep S2 on. If I keep S2 on for half the cycle, I keep S2 on for half the cycle. Half a cycle, S2 is on. Okay, this is my full switching period. So this is on for half the period, half the fundamental period, not switching period. So this is half the T fundamental or something. T fundamental. Like this is for 10 milliseconds out of the 50 Hz. I kept on for half the switching, half the fundamental cycle. I can make S1. If I put S1 on, what do I get at the output on my load? The load will have this terminal connected to this point. This terminal it will have VDC, right? But what if I switch S1 on and off? If I switch off, I will turn on S4. So what will happen? Yeah, I will have the load connected either to VDC or 0. VDC or 0. VDC or 0. Right? So I get the voltage across my load, which is my VAB voltage. It's VDC, 0, VDC. It's like the unipolar switching. Right? And if I do the opposite with the other side, I can do something that looks like this. I can vary the pulse width, of course. Right? So I get something that's also nice. It gives me something that looks like the unipolar switching, but with an advantage. What's the advantage in this case? I reduce my switching losses. This is only switching one time per fundamental period. This switch is switching all the time, that's fine. I get a power quality similar to the unipolar case, but I've reduced switching losses in one device. Right? So does this have advantages? Yes, people came up with topologies where they've mixed and matched. So they maybe they have cascaded converters, like the cascaded multi-level converter topology that we came up with, and they make one, like let's say one DC, one full bridge, one H bridge, a higher voltage than the others, right? And they make the higher H bridge, a higher voltage H bridge, switch at a lower switching frequency, because remember, high voltage, high current switches are not able to switch at very high switching frequencies. The lower the voltage and the lower the current, the easier it is to make a switch at high frequency. Makes sense, right? So if you have a very high power converter, and you would like an improved power quality waveform, you would like to switch at higher frequency, but you don't have that luxury because you cannot find the switches. So people came up with converter topologies where you can mix and match. You can make one H bridge switch slowly and produce this, right? Just something like this, right? And then I can add series H bridges with it that produce a higher switching frequency, so that maybe they can do this, right? For example, and maybe something else that does this at a higher frequency, maybe a smaller voltage, right? You're adding them in series. So here, what did I do? I produced a better looking waveform, and the one with the lowest switching frequency is a higher voltage compared to the others. So I bought the high voltage switch, high voltage, high current switch, but I'm switching it very slowly. It's okay. It can switch slowly. I use the other switches to switch fast. I can improve the power quality waveform, and I can find lower voltage switches to do that. So you see the benefit of doing something like this? Yes. I mean, this is very practical. It's not. It is used in practice. People use it in practice. So this is an example of that, right? So we're just showing you here one switch remains on, and the other switch is switching between 0 and VDC. So what do I get? Fine, I get, whenever I have this switch on, I get negative. The other switch on, the other leg, I get my positive pulses, right? That's the description I was just going through right now, right? So two of the switches in the power converter are switching slowly. The rest are switching fast. I get a similar pulse width output pulse width modulated waveform like the unipolar, very similar to the unipolar in shape, right? With a benefit. Okay, so we would like to see this carrier waveform. We call this the carrier waveform. The triangular waveform we call the carrier waveform. We call it the other waveform. We call it the modulating waveform or your reference waveform. So, can I make the modulating waveform larger magnitude than the carrier waveform? Can I make the sine wave here have a peak that is greater than the triangular waveform? If you do that, what do you get at the output?
Smaller for each pulse. Pulses will be smaller because the condition is the triangular greater than the sensor.
Okay, let's look at let's go back to our comparator example, right? Let's look at our comparator thingy here. I have my triangular waveform here, and I have my sine wave here, right? If I make this is my triangular waveform. This is half. And then I make my sine wave like this, right? If I make the triangular waveform higher frequency, it makes more sense. Because here, fine, if I make the triangular waveform higher frequency, then what's going to happen here? There will be intersections with the red waveform. How about in this area? There will be no intersection, so it will not be switching. If it's here in this case, if the sine wave is higher than the triangular waveform, I'll get a high. If it's lower, I get a low, right? So maybe what will happen is you will get something that looks like this: some pulses, and then no pulses, and then some pulses again when you start intersecting with them again, right? So this converts the pulse width modulation into a nonlinear type of pulse width modulation, right? So if my peak for the sine wave, which is my reference waveform, is less than my carrier waveform, then my fundamental output peak is directly proportional to the DC voltage I'm putting. Actually, for a full bridge converter, we said for a full bridge converter, what is the output voltage range? Plus and minus VDC. Right, for a full bridge, 1, 2 on, VDC, 3, 4 on, I get minus VDC, correct? So my peak value for the output is VDC. right? So the peak value for the output is VDC. This relationship between peak value for your fundamental output and your DC voltage is related by something called the modulation index. This relation is related, these two are related. Your output peak value and your DC voltage are related by a modulation, what is a variable called the modulation index. It's an indication of the magnitude of your output, right? If the modulation index is equal to 1, what does that mean? It means that the peak value of my fundamental and the peak value of my DC voltage are the same, right? That's what this means, yeah. So this does not apply to this case where my modulating waveform is greater than my triangular waveform, right? In this case, I will not get a linear relationship between these two, right? Because at some point, the value of V1 and VDC will no longer be related by a linear variable, right? If V1 becomes less and VDC is the same, is that necessarily because I've reduced V1? Let's say here, if I reduce the magnitude of the sine wave a little bit, what's going to happen? This waveform will look maybe like this, fixed but for a little bit less time, and this. But what I'm saying is that this fixed amount of time will produce a certain value for your peak value for the fundamental voltage, right? If I do this, I take this, and do a Fourier series and find the fundamental value. I will get a certain fundamental value, right? That value will not be linear, right? It will not change linearly. If I decrease this by 10%, right? The value of V1 will not decrease by 10% if your red waveform here is higher than the yellow waveform. But if this red waveform is less than or equal to your triangular waveform, then any change is linear. If I decrease the modulation index, or if I decrease the value of the sine wave, I get a fundamental here that is 10% less if I decrease this 10%. And so on. It will be a linear change. Otherwise, it's nonlinear. Do you see what I'm saying? Yes? No? So anyway, so this amplitude modulation ratio, yes sir? Yeah, of course. People work a lot on nonlinear modulation because what happens if you, what's the difference between this and this from a fundamental output perspective? Which will give you a higher fundamental output? Huh? The one below, right? So sometimes you would like to get a higher fundamental output, right? So you would go into the nonlinear region of the modulation, but it may come at the expense of what? Here I have less pulses or more pulses than this? Less pulses. So it may come at the expense of power quality, right? So you may be able to get higher voltage, RMS value, but lower power quality. So people do that. If you want to run motors at higher speeds, for example, you want to utilize, you have a DC voltage. You would like to utilize it to the maximum that you can, right? You know that if you go into that region, maybe if you have a motor application that requires very low torque ripple, that you are actually in fact adding torque ripple intentionally because you're decreasing the power quality that you have. But if your application allows it, you can do it, right? So some people will operate in nonlinear. So there is a lot of people worked on nonlinear pulse width modulation algorithms as well. Okay, so the ratio between the carrier or the triangular waveform and my reference is called the frequency modulation ratio. I would like that to be what? We said if the carrier is a high frequency and your reference is a low frequency, then it's like the Shannon's sampling theorem, right? If I have a lot of pulses, if I sample many, many times, I can reconstruct my waveform better, right? So theoretically speaking, the higher MF is the better, theoretically speaking. But it also means that you have to switch many, many times, right? So it affects your switching losses, so this is one parameter, one of the design parameters that we choose. One of the design parameters. And it will also affect what? It will also affect your power quality. It will also affect your power quality. So people found that also if it's not just the magnitude of MF, also the value of MF. MF can be, let's say the frequency can be of the carrier can be 3 times the frequency of the reference. In three-phase power converters, when we do the Fourier series, we'll find that if you choose MF to be a tripling multiple of your reference waveform, then you get better harmonic content. Right? From the Fourier series, I will show you the equation later, but you can choose it as whatever you want, but you would like to choose it so that you are able to construct a sine wave with good power quality. That's what you want to do. So people found ways to, okay, do I make the carrier over the reference 90 or I make it 80? Do I make it 20 or I make it 10? Right? Fine. Besides switching losses, what does this affect? It affects power quality. So, the obvious thing is take this, do the Fourier series, and find the relationship between the carrier frequency and the reference frequency ratio, so that I do a better power quality. So people worked on that for a while, and they've come up with recommendations for how do you choose MF. If it's a tripling multiple of the reference, then it produces better power quality. For where does that come from? From the Fourier series. Okay. So this is a design parameter, and this is also a design. This is a control parameter, right? You would like to control in an AC drive. You would like to control your magnitude and frequency. How do you control frequency? By duty ratio, right? You create a duty ratio that of a sine wave that is, fast or slow. You can create a high frequency sine wave or a low frequency sine wave. That's fine. Right? This is your duty ratio. You can create a duty ratio for a high frequency sine wave or a low frequency sine wave. And that's how you control the frequency of your output. But how do you control the magnitude of your output? You control the magnitude of your output using this equation. Right? Using the modulation index. So the modulation index is a ratio between the output fundamental to your DC voltage. Basic. In simple terms, what is that? It's basically the magnitude of your duty ratio. So I want to produce something with the same frequency as this waveform. This is 0 to 1 duty ratio, right? But lower magnitude. How do you do that? You create this. Right? This is intersecting with your carrier waveform, all these triangles, right? And you create something, but you created something with a lower fundamental, right? By choosing a lower modulation index. So now I can control frequency by changing my duty cycle's output voltage frequency, and then I can control also magnitude by changing my duty ratio as well as a magnitude, right? But the carrier will not change, right? The carrier, this triangular waveform does not change. And that's fixed. Yes, sir.
The thing is we're using this positive modulated signal to control gates, right?
Yes.
How does that influence the output voltage? Because it's just switching.
Okay. So it's good. So now this is my actual circuit, right? Here. So here I put my gate drive circuit. So this is called the gate drive. And this is basically an amplifier. This is basically an amplifier. This is my gate drive circuit. Before my gate drive circuit, I have my processor circuit or my duty cycle generating circuit. So the duty cycle generation can be from, as we saw before, from a microprocessor, from a comparator, with comparing the triangular waveform to my reference waveform, whatever you're bringing the duty ratio from. The output here is a pulse width modulated signal that's controlled by duty ratio, right? We saw how to create that. This goes to what is called the gate drive circuit. This gate drive circuit is typically a power supply, and this power supply is supplying power to a circuit that is amplifying your duty ratio generated pulse width. So maybe you have a pulse width coming from your processor that is 0 to 1.3 volts, right? This is coming from your output, digital output on your processor, 0 to 1.3 volts. You've created that, you've created this effect internally, the comparison between your triangle from your timer and a lookup table of a sine wave. You create that inside your processor. You took that to the digital output, producing 0 to 1.3 volts. This is not going to run a MOSFET. If you look at the MOSFET datasheet that we have, typically gate voltages are in the range of 15 volts, 10, 15, 12, 10, whatever. So you need something to take this 0 to 1.3 volts, and this is also, your processor is not able to source power. If you look at closely at the processor's datasheet, they will tell you that the processor's pin is able to source and sink very limited amount of power in milliwatts and currents in milliamps, right? So that is not something you can utilize to run a power device. If you look at power device gate drive currents, they're pretty high for a short period of time, but pretty high. You cannot get that from a processor. So we have to put an amplifier stage. This amplifier is called a gate drive circuit. So this gate drive circuit can be, for example, it can be another set of two switches like this. That's one thing it can be. Let's say these two switches powered from an external power supply that you have provided, and then these are low voltage MOSFETs or low voltage BJTs. That's fine. You will provide one here and its complement. So one here and then maybe its complement, and its complement to the other device, and then they would be switching. If the bottom one is on, you get 0, right? How the top one is on, you get VCC that you have, the 15 volts, right? So this gate drive circuit, simply the gate drive circuit can be basically a small version of your power converter. It's a small power converter, but it's because a power converter is an amplifier at the end of the day, right? I would like to take 3 volts, make it 9. It's an amplifier. 9 volts, create 3. It's an amplifier, but not making the signal large, making it small, right? So in its simplest form, this is a simple gate drive circuit. So this is required. So we have a simple gate drive circuit here. One thing to note, of course, that these gate drive circuits are very tricky because here, this needs to be an isolated power supply because I need to supply a voltage between the gate and source of the device, right? How do you turn on a MOSFET? I provide VGS. Remember your 325? The curves for VGS versus ID typically here, ID versus VGS, right? With these curves, ID versus VDS, sorry, ID versus VDS, right? At various values of VGS, right? So here's the 325, right? It's ID versus VGS, versus VDS at various values of VGS, right? So you're providing a gate to source voltage here, a gate to source voltage equal to a certain value to be able to switch the device on to conduct a certain current and have a certain voltage across at VDS. This is DS. This will be VDS across the device when you switch it with a certain VGS. Right, this is VGDS. So this means that the gate voltage is with respect to the source. It's not with respect to the reference here. Right? That's why the power supply that is going to provide voltage to this gate is going to be providing voltage, let's say 15 volts, above the source voltage level. Right? Above the source voltage level. So you cannot just, let's say, take this same DC power supply and supply this gate with it, and then also supply this gate with it. You cannot do that, because if you do that, this power supply, let's say, is 15 volts. This 15 volts that this power supply is providing to run this small amplifier is providing 15 volts with respect to the reference. not with respect to this source. It's providing 15 volts with respect to this source, right? This is gate, drain, source. So this 15 volts, if it's with respect to this source, so it will make this thing work. So you can put a power supply with respect to this reference, and it will be able to run this gate drive circuit no problem. But you cannot have a power supply running this gate drive circuit and running the top gate drive circuit at the same time, because you're trying to produce a voltage at the gate with respect to the source that is higher than the source value, right? I don't know if it's clear or not.
My question was, why we are changing the amplitude of the modulated signal, the sine wave? I know about the gate drive, it's just, I mean, the signal, assuming we have a signal of
0 to 1.3.
Even higher than that. I mean, aren't we controlling that amplitude?
No, you're not controlling that amplitude. No. You're controlling the width.
Yeah.
You're controlling the width out of the processor.
Yes.
And then with the gate drive, what you're doing is controlling its amplitude as well as power capability, not just amplitude. It's you can, because the power, let's say you have a processor that can produce 15 volts, but the processor cannot produce power, right? The processor is made to produce signals, not power. So the gate drive circuit is made to take a signal and convert it to a powerful amplification of that signal that you put in. I don't know if it answers your question.
V1 is not actually a value of magnitude, it's the average value of this.
What?
V1.
V1?
V1
What's V1?
from the left side. So V1
V1 is the peak value of your fundamental. The peak value of your fundamental.
that's the sine wave?
Yeah, your sine wave. The sine wave that you want to create, it has a peak value that is equal to V1. V1 over your DC voltage is equal to your modulation index. If your modulation index is 1, what does that mean? It means that you have created a fundamental that has a peak value of VDC. Okay? So everybody's clear on frequency modulation ratio and amplitude modulation ratio? Just the ratio between the triangular and the reference sign. And the sign, reference sign, and the triangular carrier. This controls what? Switching frequency. Right? This will control switching frequency. This controls magnitude of the fundamental. Right? One controls switching frequency, and one controls magnitude of the fundamental. Okay, so we said that. How do you choose MF? We choose MF such that we want to improve the harmonic content, right? Or how do you design a pulse width modulation algorithm? You design it such that you improve harmonic content. So what is our measure of harmonic content? Always Fourier series, right? So how do you find the Fourier series for, this is bipolar modulation. Bipolar pulse width modulation, we go between minus VDC and VDC, right? So before, what we did was what? We took one pulse and found the Fourier series for that if we add some alphas, add some phase control at the beginning and the end. Very similar thing here. Here, I would like to now find the Fourier series for this waveform. How do you do that? It's very complicated, right? Because, fine, this whole thing is periodic, but also within this big sine wave, within this big periodic waveform that's happening every 50 hertz, this is also a periodic pulse. This pulse is repeated periodically every period as well. So how do we find the Fourier series of something like this, right? What we do is we take each pulse and we find the Fourier series for each pulse and then add the Fourier series for all the pulses, because the pulses are periodic. It happens here, happens the next cycle, happens the next cycle, happens the next cycle. So it's a periodic non-sinusoidal waveform, right? So how do I find the Fourier series for it? I can do that. For one pulse, I know how to do it. How about if I add another pulse? Well, if this other pulse is also periodic, happening this cycle, next cycle, and the following cycle, I do a Fourier series for it by itself, and then add them together. If I add them together, they will contribute to the Fourier series of the full waveform that I have here. This full waveform will have a fundamental, will have a second harmonic, third harmonic, fourth harmonic, fifth harmonic, and that's what we see here. Here, what they did was, for bipolar switching, they took one of the pulses, and they did the Fourier series for one of the pulses. This pulse is defined by a few angles: alpha k plus 1, delta k. They define the pulse by various angles. We know how to find the Fourier series for a single pulse from like the phase control example that we did before. They know how we can derive the Fourier series for a single pulse, single repetitive pulse. We can do that. And that's what they did. For one of the pulses, k, I can find the Fourier series, and that Fourier series will have fundamental, second, third, fourth, fifth, etc., etc. And then I can do this for various values of various pulses. So this is for one pulse. I'll take the next pulse in the pulse width modulation cycle, and I'll do the Fourier series for it as well. How is this second pulse defined? It's also defined by a set of angles, right? Of course, the angles will vary depending on the type of pulse width modulation that you use, but generally this is the Fourier series for one pulse. This is the Fourier series for your full pulse width modulation waveform. It's basically a summation of the individual Fourier series for the single pulse that we have in the waveform. Does it make sense? So, of course, it's good to tabulate some of these results, right? So now I would like to look at, for n equals 1, for my fundamental, I would like to look at the contribution of all these pulses to my fundamental. So at the fundamental, if my amplitude modulation ratio is 1, right? What is this ratio Vn over Vdc? Vn is what? Remember, Vn is the magnitude peak value of my fundamental. Peak value of my fundamental. If my modulation ratio is 1, then V1 is equal to MA times VDC. So it's equal to 1, right? If the modulation index is 0.9, it's 0.9. Remember, we said it's linear. If the modulation index is less than the peak value of the triangular waveform, then V1 and VDC are related by V1 is equal to MA times VDC. I'm trying to find V1 here over VDC ratio. So at various values of MA, of course it's the same, right? Because this is linear, right? We said if this is linear, if this is 0.9, that means MA is 0.9, right? And that's why you see this just doing this way, right? At the various values of modulation index, right? How about at the n equals the switching frequency? MF is the switching frequency. If MA is 1, what do you expect? This is a harmonic, right? You expect the harmonic to be less than or greater than your fundamental. This is at modulation index of 1. So here I have what? I have my sine wave. At the modulation index of 1 means I'm intersecting that with a triangle, right? And I'm producing a pulse width modulated output. This pulse width modulated output will look like something like this, right? Let's say if this is, this is bipolar, so it will look like, like the bipolar output waveform. This bipolar output waveform will have a fundamental, right? Obviously, it's my reference waveform here, the black waveform, is my fundamental at the same frequency of my fundamental output. So, do I expect, if I do a Fourier series or an FFT for this bipolar output, do I expect to see something at the fundamental or not? I better, right? Because that's what I'm trying to create here. What also do I expect to see dominant in the waveform? I expect to see harmonics. At what frequency? At what frequency? At what frequency is this? Am I switching? At the same frequency as my triangular waveform, right? So I have things changing at a certain frequency. Do I expect to see that on the spectrum of the waveform or not? If I do Fourier, what is Fourier series? Fourier series is I have a waveform that is periodic, that is not sinusoidal. This waveform, I'm doing something at the fundamental frequency. So if I do FFT, I should see fundamental frequency. Also, this waveform has a lot of switching at some frequency, right? What is this frequency? It's my switching frequency, right? If I'm doing this triangle, if I'm creating this triangular waveform, intersecting this black waveform, creating pulses that are changing at that same frequency as my triangle, then I expect to see that in the harmonic spectrum. I expect to see it. And that's why we wanted to tabulate what happens to my ratio of my fundamental, or now here it's V at the voltage at the switching frequency to my DC voltage for various values of MA. For various values of MA. So let's say I put MA 0.9. What is the voltage at my switching frequency? At my fundamental it was 1. How about at my switching frequency? Do I have a voltage? Do I see something in the spectrum there? Yes, I will. Because I'm switching at that frequency, I expect to see something there. Right? What is the value of that? It just happened to be 0.6. Where is that coming from? Where is this 0.6 coming from? From this Fourier series. Right? You calculate V of MF. Right? V of MF. Where at a ratio of VDC over V1 equals to 1 in this case. Yes, sir. MF is your frequency modulation ratio. It's not arbitrary. If you're looking at it from a design perspective of your power converter, it will dictate your switching losses. If you're looking at it from a power quality perspective, we said that if you do the Fourier series, you will be able to produce a better quality waveform if MF is a tripling harmonic. Yes. Yeah, it's arbitrary. Yeah, it's arbitrary. It's an arbitrary value. Yeah. You're just trying to find the ratio of VM over VDC. So VMF, basically. How do you find VMF? Here, this is the N here, remove it and put MF. If you're switching at 10 kilohertz, this will be the V at the voltage at 10 kilohertz. Right? So this N will be 10 kilohertz. This N will be 10 kilohertz. All the N's will be 10, the 10th kilohertz harmonic of your fundamental. Right? So you can calculate V at any frequency, right? You can calculate the fundamental. V1, V2, V3. These are V2 is what? Second harmonic of the fundamental. V3, third harmonic of the fundamental. V4, MF, V of MF is the MF harmonic of the fundamental. So I can calculate that using this equation. What I'm trying to show here is the following. What I'm trying to show is, if you notice, when you decrease the modulation index, what happens to the harmonic content versus your fundamental? Yeah, you have harmonics, you don't have fundamental. It makes some sense because, okay, if you are reducing your fundamental waveform, here, let me reduce the fundamental waveform. I want a sine wave that is very small. Okay? I do the FFT for that, versus a sine wave here that is very large. Okay? Let's do the FFT, graphically speaking. What do you expect the FFT to look like? And this is my fundamental, 50 Hertz, for example. I expect the blue to have a large power spectral density value, like a large value for my fundamental. Right? At 50 Hertz, I expect this waveform to have a large power spectral density or a large magnitude at that frequency. How about this red waveform? I expect it to be small. Right? So if I have a low modulation index equal to 0.1, it means I have this kind of red waveform. Right? But how did I create this red waveform? With pulse width modulation. I created it with pulse width modulation. I don't have a magical way to create it. I have high voltage. I want to create a sine wave output. I will use pulse width modulation. What does the pulse width modulation look like to create the blue waveform, and what does the pulse width modulation look like to create a red waveform. For bipolar switching, it will still be switching between VDC and minus VDC. But to create this red waveform, I will do something like this. Very small pulses. Small pulses. Small magnitude pulses, right? I have smaller magnitude pulses on the positive side, right? And then I will also, I'm doing my switching, I still have to do the switching because the only way to create an output is to switch my power converter. 1, 2, 3, and 4. 1, 2, and 3, and 4. I have to switch. When I switch, what happens? I have harmonics due to switching. These harmonics are pretty big, right? But when I produce a magnitude that is very low, the ratio of my harmonics to my fundamental, V1 to VDC, versus V at my switching frequency to VDC, right? If I'm looking at the value of my harmonics to my VDC voltage, what? At low modulation index, I don't have the output is very small. That's why the output becomes very small, but the harmonics are pretty large because I'm still switching. I don't know if it makes sense or not. Basically, you don't have a signal, you have noise, right? This is what this means. Because you wanted to create a small signal, but what's left? A lot of noise. Not sure if it's clear. How about what happens at the switching frequency, at the frequency of MF plus minus 2? So let's say your switching frequency was 10 kilohertz. So how about 10 kilohertz plus 1 kilohertz and 10 kilohertz minus 1 kilohertz? You have harmonics around the switching frequency. And these exactly at MF, and you have at multiple harmonics of the MF as well. So you will have, with bipolar switching, you will have your fundamental, and you will have harmonics around MF exactly, and at around MF plus minus 1 harmonic. Right? How about this is bipolar. How about unipolar? What do you expect in unipolar? We said unipolar would provide better or worse power quality. Huh? Unipolar versus, this is bipolar. Better power quality. What would be better than this? What is better? Better from a power quality perspective is what? No low order harmonics, right? Better power quality means no low order harmonics. So if my first harmonic here is at MF, do I expect that with unipolar switching I get the same, or maybe I shift this to higher place? It's the same switching frequency, but it's, remember that in the buck converter when we were doing the interleaving, what was happening with the interleaving? Interleaving when I had two switches pushing current in the inductor, and I phase shifted them and added the current. What was the effect? The effect was lower ripple. I don't know if you remember if you in chapter 6, when we had interleaved converters, the result was lower ripple. This lower ripple was going then into my capacitor. If I had lower ripple going to my capacitor, I was able to choose a smaller capacitor. Here it's very similar. I have a better power quality waveform. Of course, you can, if you have to do the Fourier series to get to this, but if you do the Fourier series, you will find that the dominant harmonic after the fundamental in unipolar switching is happening at 2MF. Right? It's 2MF and then 2MF plus minus 1. So this is 2MF. So this is happening at what? It's not very clear here, but let's say this is 2MF. Plus minus 1. So this is 2MF plus minus 1. Here. There's a fundamental, and then there's 2MF plus minus 1. So if this is 2MF here, right, plus 1 harmonic, you will find, so let's say 10 kilohertz was your switching frequency. That's MF, right? That's MF. If you add 1 to that, so 11 kilohertz, you will find the harmonic. And if you subtract 1 from that, you will find the harmonic. What is the value of that harmonic? It's 0.18 of the VDC voltage. How do you calculate that? From the Fourier series equation. I don't think I put that for the bipolar, for the unipolar case. I don't know if it's clear or not, but basically, if you have higher order harmonics, you have a better quality waveform. Because why? Because you have higher order harmonics and you have an impedance. This impedance will be higher value at higher frequencies, right? So if you have a voltage at a higher frequency, you don't care. If you have voltage at a low frequency, it's a problem because you will apply that voltage to the impedance. Impedance at low frequency is a low value because we're talking about inductive impedance, omega L. Omega L will be small versus omega L at high frequencies is a large impedance. So you will have less harmonic current in that case. Less harmonic current then means you have less torque ripple, less light flicker, less whatever, less phenomena you don't want. So unipolar switching, we said, will produce something that looks closer to a sine wave, and yes, it does, because the first harmonic is at double the switching frequency, not at the switching frequency like the unipolar case. Right? That's the difference between these two. Yeah. So we'll stop here. I think the next class, maybe I'll go through an example on these numbers on the table. Yes? Huh? Yeah, there's one more class. There's one more class. We can skip it, but I prefer to talk. I mean, this is very important stuff. I mean, practically, this is important. Yeah. If you work on. No, I think Monday is the last day of class. So I want to do next time. I'll do three-phase inverters because again, it's an important topic, and I want to do maybe an example on this harmonic stuff because it's also an important topic from a practical perspective, not just because it's an exam or whatever, right? So practically, it's important for you to understand that. But then also we'll do some three-phase inverters. Yeah. So we'll stop here. Next time will be the last one, hopefully.